Alright, so in this video we are going to explore the LC circuit. So we're going to put an inductor and a capacitor in a circuit together. Now we have to keep in mind that in reality there's no such thing as an LC circuit because there's always some internal resistance somewhere in a circuit. So really they're all LRC circuits, but we're going to talk theoretically about how a LC circuit would behave. So the first thing we have to do is charge the capacitor. Because you can't get energy from nowhere. So we need an energy source, which is going to be our charge capacitor. And so we end up with a circuit that looks like this. We have our capacitor, we have our inductor, so it has some C, some L. Alright, so as soon as we hook up our circuit here, the capacitor begins to discharge. So remember, we're thus transferring energy from the electric field in the capacitor to the magnetic field that is in the inductor. However, the current hasn't stopped flowing, which means the electrons go back around, and so then the capacitor begins to charge again, but with the opposite polarity. So what was once the negative plate will become the positive plate, and what was once the positive plate will become the negative plate. Keep in mind this doesn't happen instantaneously, and it doesn't happen at the same rate the entire time. As we learned in the RL circuit, the inductor hasn't affected the rate at which the current changes with time. So as the current decreases, the electric field decreases, which induces an EMF in the inductor, which slows down the decrease in current. But eventually we end up with the situation described in number 3 here, where the capacitor is now charged again, but with the opposite polarity. But then immediately the capacitor begins to discharge again. Through the inductor. And so we call this process electrical oscillation. And we're going to draw some analogies as we go through the rest of this lecture between the behavior here, where the energy is oscillating back and forth between the capacitor and the inductor, to how a spring, so simple harmonic motion behaves, so a mass oscillating back and forth on a spring, where we went from spring potential energy to kinetic energy back to spring potential energy. Alright, so now we're going to apply Kirchoff's law to our circuit. So we have the voltage across the inductor, and then the voltage across the capacitor, and that's going to sum to 0 because we have a complete circuit. Alright, so I'm going to do a little bit of rearranging here. Remember, current is equal to the change in charge with respect to time. So I can rewrite this as the second derivative. And I'm going to divide each term by a negative L. Alright, so this is actually a differential equation, so I'm just going to skip to the answer. So we're going to be able to find the charge on the capacitor at one particular interest so that's little q here. This is q, the maximum charge on the capacitor, times the cosine of omega t plus phi. Alright, so let me define a couple more terms in here. Omega is going to equal to the square root of 1 over L times C, or the inductance times the capacitance. So this is going to be the angular frequency of the oscillation. So it's telling you the rate at which things are oscillating back and forth between the capacitor and the inductor. And that's going to have units, believe it or not, of radians per second. So that means if you're using this formula, you do need to be in radians per second, or radians in your calculator to take the cosine of this particular function here. Phi here is the phase angle, and this is put in there because what happens if the cosine of t when t equals 0 is not 1? So what happens if we have a little bit of an offset? For now, we're going to assume the phase angle is 0. We'll talk more about phase angles in the next chapter. So as I said, this equation allows us to find the charge on the capacitor in one particular instance, and we defined what the frequency of the oscillation is, and it relates to the inductance and the capacitance. If I take the derivative of the function we just found in terms of t, we can get the current through the circuit at one particular instance. And so that current is going to equal this relationship here. So I've just taken the derivative in terms of t here. Now there's one more analogy we can make between springs and this particular setup here, and that's in terms of energy. So we charge the capacitor, and so we have the potential energy due to that charged capacitor. And as it begins to discharge, we get some of it being energy stored in the inductor and some of it being energy stored in the capacitor. And we oscillate back and forth in between the extremes. Well, if I rearrange this and solve for current, the current in the potential energy for the inductor, I get this particular relationship here. Which allows us to see how the current changes as the charge oscillates on and off of the capacitor. So we have several relationships here that allow us to describe an LC circuit.